So as a reminder, last time we started talking about equivalence relations. And what we said in terms of an equivalence relation is, well, we actually don't have that one up here. So let me go, can I go backwards? Come. We're supposed to go backwards. There we are. All right. So what we said was equivalence relations were relations that had 3 out of our 6 properties. Can they have more than 6 properties? Definitely, but they have to have these 3 properties of the reflexive property, the symmetric property, and the transitive property. Now, the reflexive property says you have to have all of your ordered pairs, A, comma, A, inside of your relation. Remember, that's the same thing as in the diagraph representation. You have all of your loops. Symmetric says if, and notice that's a big if right there. If you have some ordered pair A, comma, B in your relation where A and B are not the same element, then automatically you have to have the reverse. In other words, B, comma, A. Notice, though, nobody specifies that A and B are different, because if A and B are the same, all that says is you've got a loop. And with the symmetric property, it's totally fine if you have loops or not. Now, in terms of the digraph representation, what this means is if there's an arrow between 2 vertices, you have to have both directions of the arrows. In other words, you have no arrows between vertices, or you have all or both of the arrows between vertices. And the last thing is the transitive property. The transitive property says if you have 2 ordered pairs, and the key thing with the 2 ordered pairs is you have to have a common element in the second position of one of them and the first position of the other. So if those ordered pairs, both of them are in your relation, then you should be able to find somewhere else in your relation the ordered pair of A, comma, C. Or in terms of the digraph, if you can find some length 2 path, and here when I say path, we're not doing it in the proper graphical sense. We're doing it in the sense that you have 2 arrows strung together. You can always then do what? You can always then find a 3rd arrow that's essentially like a shortcut. Okay. So those were our 3 properties of reflexive, symmetric, and transitive. And if you have all 3 of those properties, then you're an equivalence relation. Note, equivalence relations essentially act like the equals operation. That's one of the claims to fame in terms of why people really like equivalence relations, is because of what they do is they essentially say if you've got some element related to some other element inside of an equivalence relation, that essentially tells you that those 2 elements they don't have to be equal, but they essentially act like they're equal inside of that set. Weird, but true. Okay. So that's our reminder of our definition. What we ended on last time was the definition of equivalence classes, and then we didn't get to an example on that. So let us go now to equivalence classes. And this was the thing I had prepped up before. That was a little too early. All right, so an equivalence class of some element is specifically you pull an element from your building set, where A here was your building set of your relation. The name equivalence class is only applicable if you actually have an equivalence relation. So if you don't have the equivalence relation, you can still build this same set down here. This set that you build is applicable for any relation, but it's not called an equivalence relation. It's called the image as opposed to an equivalence class. Okay? So the equivalence class of A from your building set is defined by these square brackets, and those square brackets means equivalence class of A. And it's defined to be all of the elements from your building set A, where A is related to this element B. In other words, you collect all of the second position guys from your ordered pairs, where you're only looking at the ordered pairs whose first position is whoever A was. Okay? So that's the idea behind the equivalence class. Now, in terms of what this means, roughly speaking, what this means, if we sort of in our heads zoom back to equivalence classes, we're roughly doing the same thing as the operation of the equal sign. This means that this equivalence class of A is, roughly speaking, all the elements equal 2A. Now, please note, I put the quotes around equal because the official term is equivalent, and that's because they don't have to be equal. Equal means exactly the same, but it's acting just like an equal sign, or similar to an equal sign. An equal sign is actually a specific equivalence relation. Now, the quotient set symbolically is the letter A, your building set, a slash. This isn't a fraction, it's sort of a slash. And then after the slash is R, the name of whoever your relation is. This guy is a set of all your equivalence classes. So the technical definition of this guy is you have the quotient set equals all of your equivalence classes of A. Note here, if you actually write this out, this would be something like equivalence class of A, equivalence class of B, equivalence class of C, etc., where your building class A would have to include, your building set A, would have to include all of those elements that are inside the square brackets. Now, what do we know about sets? We know you don't write down duplicated items, so if some of these equivalence classes are exactly the same, hint, they almost always have some duplicates, you don't actually write down the duplicated elements. And this is why people really look at the cardinality of the quotient set, which is just a fancy way of saying how many distinct or different equivalence classes of A exist. Okay? So that is a ton of theory. Let us go ahead and jump now into some examples. Okay. So the first example that I've got for us is this guy. Our building set is simply the numbers 1, 2, and 3. The relation is 5 ordered pairs, all built from those numbers 1, 2, and 3, and it's the ordered pairs 1, 1, 1, 2, 2, 1, 2, 2, and 3, 3. And one of the things that sometimes, well, if you weren't inside of a class situation, the first thing that you would have to do here is you would have to actually figure out, is this relation right here an equivalence relation? So that would actually be your first step. Now, at this particular moment in time, since I have this first question is find all the equivalence classes of A, the underlying assumption that I totally should have written right above part A here is this relation already is an equivalence class. But since I didn't write that, let us actually check to see if it is an equivalence class. So I'm going to go ahead and over here to the side actually draw out the digraph of this particular relation. So I'll go ahead and take our building elements 1, 2, and 3. In terms of our ordered pairs, we have 1, 1. We have 1, 2. We have 2, 1. And we have 2, 2, and 3, 3. Okay? Now, in order to be an equivalence relation, you have to be reflexive, symmetric, and transitive. Okay? Now, unlike when we were checking if a relation had all of our properties, if all you want to know if your relation is an equivalence relation, you don't have to check all 6 properties. All you have to do is check those 3. Okay? Now, remembering what the definition of reflexive is, what do you think? Is this particular relation reflexive? Hint, the answer is either yes or no. Reflexive. Yep. So this guy is totally reflexive. Hint, remember how I said a few seconds ago, or maybe close to a minute ago now, that this guy was actually going to turn out to be an equivalence relation? That totally gives away the answer for each of these upcoming questions. So yep, this guy is totally reflexive, and you can see that either in the picture or in the ordered pairs. If you're looking in the diagraph or the picture right here, we've got loops on every single one of the vertices, so totally going to be reflexive. Or in the ordered pairs, you've got all your doubled up, all of your 1, 1, 2, 2, 3, 3 ordered pairs. Now, what about symmetric? What do you think about symmetry? Does this guy have that symmetric property? Don't overthink it. The answer is either yes or no. And I'm totally waiting for you guys to send in answers. As a follow-up, I'm going to immediately ask why to our answer of either yes or no. So think about that while you're thinking about yes or no. So what do you think? Is this guy symmetric or not? All right, so we got one guess in. We got two guesses in, and our two guesses are completely opposite. Three guesses in. We're still close to 50-50. Not really with three. You definitely have a winner. Anybody else have a guess? All right, I am not seeing any other guesses coming in. The actual correct answer here is yes. So the question is, how do you tell, how do you tell if your relation is symmetric or not? So the key thing to look for in terms of symmetry, remember symmetry was you take any one of your ordered pairs and you check to see if the opposite one is there. Okay? So if we look up in our ordered pairs, you can ignore all the guys that are duplicates. So our 1, 1, our 2, 2, and our 3, 3, you can completely ignore. Now, with symmetry, you do what? You look at the ordered pairs that don't have the same element. So for example, 1, 2. Then look elsewhere in your relation and see if you can find these exact two numbers but the order reversed. Notice we totally have that right there. And then you check that same exact criteria for every single ordered pair in your relation. In our case, we only have two of them that their first and their second positions are different. And those two guys, the 1, 2, and 2, 1, are exactly the same numbers but the order reversed, which means you're symmetric. I personally find symmetry easier to see in the digraph. So notice here in our digraph, we have what? We have loops on all of the vertices. We don't care about those loops. What we do care about is the actual proper arrows that are not loops. We only have arrows between the vertices 1 and 2. And notice we have both of these two guys. So symmetry says if you have any arrow living between two vertices, you need to have both directions. We have both directions. Now, we are missing arrows between 2 and 3 and 1 and 3, but that doesn't change the property of whether it's symmetric or not. All that says is it's a different equivalence relation than if you actually had arrows over here that we're currently missing. So at this point in time, we have what? We've got the two arrows going between 1 and 2, so we are totally going to be symmetric. Okay? Now, in terms of transitive, it does turn out that this type of figure right here is transitive. Transitivity says you have to have two, you take a path of length 2 or two arrows stacked back to back, and there always has to be a way to get from your starting point to your ending point in one arrow. Here, if you started with the loop, the only way you could get a length 2 path, or really two arrows stacked next to each other, technically speaking, we should probably call that a length 2 walk, is 2 loops. Well, you can definitely do that in one loop because you're still starting and stopping at the exact same spot. If you took two arrows over here, you could, again, do 2 loops at each of these endpoints, no worries. But if you actually used guys that were not arrows, here, from 1 to 2, use 1 arrow. At 2, you could use a loop. Well, that's the same as if you didn't use the loop. Or you could go 1 to 2 and then back to 1, and then going 1 to 2 and back to 1, doing it in 1 arrow would be using the loop. So it turns out this guy totally is also transitive, which you can also see by throwing this into the matrix representation, which we talked about at the end of last week. Okay? So this means that this guy is totally an equivalence relation. Okay? Now, once you've established that it's an equivalence relation, or if somebody tells you it's an equivalence relation, then you're ready to go ahead and find your equivalence classes of A. Now notice here your building set. Your building set is 1, 2, or 3. The equivalence classes of A are only going to be corresponding to your individual building elements of A. So for example here, the only possible equivalence classes that we're going to have in play are the equivalence classes corresponding to 1, 2, or 3, because they're the only guys actually in this set A. Now, to talk about equivalence classes, you put the notation in, which is just those square brackets, and then we actually have to figure out what these guys are. Okay? So what do you guys think? What might be the equivalence class of 1? Actually, let's do the equivalence class of 1 together, and then I'll ask you guys about the next two. So the definition of an equivalence class was to find all the elements from your building set where the element that you're going to pull is the second position, and the number inside whoops, I do not want that last curly brace. And the number inside right here, or the number inside the square brackets, excuse me, is the first position of your ordered pair. And that's got to be somebody inside your relation, okay? Now, if we actually write these guys out, notice we're looking for all of our ordered pairs in our relation that start with a 1, and we just want to strip off all of the second positions. So here, we would go up to what? We would go up to 1, 1. Well, the second position there is a 1. We'd go up here to 1, 2. The second position here is a 2, so we'd pull off the 2. And notice there's no other ordered pairs that start with a 1, so we stop at just the 1 and the 2. Okay? And that's it. It's literally all you do. It's just stripping off those second positions. Now, notice what's going on. Well, I shouldn't say that yet. We'll do it when we finish this off. So if we want to do the same thing for the equivalence class of 2, any guesses who the equivalence class of 2 is? And while you guys are thinking about what numbers actually go in the set that corresponds to the equivalence class of 2, I'm going to write down the same definition right in front. Any guesses what should go inside the equivalence class of 2? Yep. So it would be 1 and 2, just like before. So here, for the equivalence class of 2, you're going to look at who? You're going to look at all the ordered pairs that start with a 2. So there's 2, 1, and there's 2, 2. There's only 2 of them. And when you strip off those last 2 numbers, you're just going to get a 1 and a 2. Notice here, the square bracket guys, the equivalence classes, come straight from your building set. But so do the actual elements in each of the equivalence class. You're never going to get an element over here that's not in your building set. Now, will you get all the elements from your building set? No, not necessarily. We didn't get a 3 in either one of these cases. But you're never going to get some element like a 4 or an actual ordered pair like a 2, 2 inside of here. Okay? So these guys here, these equivalence classes, are subsets of your building set A. Now let's finish this off. If we go ahead and down here for equivalence class of 3, what do you guys think the equivalence class of 3 is? And while you guys are typing, I'll go ahead and write out the descriptive definition here as well. Anybody got to guess what should be the elements of the equivalence class of 3? That last one. You guys totally nailed it. It is just the number 3 because you're looking for all of the ordered pairs that start with a 3, and we literally just have that 1 there at the very, very end. Now, if you have an equivalence relation, you always have all your doubled up ordered pairs. You always have 1, 1, 2, 2, 3, 3, etc., which means your equivalence classes are never going to be empty sets. Why? Because the equivalence class of 1 will always be pulling from the ordered pair 1, 1, so it'll always have the element 1 in it. The equivalence class of 2 will never be empty because you'll always have the ordered pair 2, 2. So you'll always have the number 2 inside of it. And the equivalence class of 3, in this case, was close to being empty, the smallest it could ever be, which is to have itself inside of there. In other words, 3, 3. Okay? So that's how to build equivalence classes. It literally is no harder than that. The only time it can feel harder than this is if your relation is really big or maybe it's given by a word description. But in terms of what you do, that is exactly what you do regardless of the equivalence relation you have. Now, if we then push this out to say, to asking the common question that people typically ask, which is how many different equivalence classes do we have? In other words, what's the cardinality of this guy? You want to go back and start thinking about, well, what is the actual set, the quotient set here? So if we actually look at the quotient set, and please note, I'm not actually doing cardinality right now, you can, by default, just dump all of your equivalence classes. In other words, put square brackets around all of your different elements from your building set A. This here, that's okay. That equals is true. Now, is it helpful for cardinality? No. Okay. So what I've done for this particular question is I went ahead and threw it up in a poll everywhere question, but it didn't actually get embedded into these slides. So if you go to, and I'm going to go ahead and tag it right here for us. If you go to our standard poll everywhere location, see if you can guess how many distinct equivalence classes there are, or I should say, what is the cardinality of our quotient set. In other words, we want to know how many elements are in this quotient set. So see if you can figure that out. And I'll go ahead and share that screen with us. Oh, actually, about half of you have already answered, so I almost feel like I don't need to share that screen with us. We'll unshare that in just a second. But that also gives you the URL as well. Oh, it looks like about 2/3 of you have answered. What about the rest of you? Got a guess? It looks like 3 people haven't made a guess. So I'll give you guys a little bit more time to make a guess, and then we'll confirm. All right, it looks like the guesses have stabilized. So let us see what you guys have guessed. Ooh, there's all sorts of guesses all over the place. All right, so before we actually say what the right answer is, let us go ahead and evaluate the possibilities. First question is, before I go too far into evaluating these possibilities, can you actually see that second screen large enough for me to wiggle my cursor in front of it and talk about the different guesses that we have right here? Or do I need to blow up the shared screen a little bit bigger? Can you guys see it okay? All right, I don't see any no's coming through, so I'm going to go ahead and keep it currently just because with the PowerPoint in the slideshow format, it's difficult to switch easily between the things. All right, so you had 5 choices here. You had 4 choices that were somewhat believable, and you had 1 choice that was a complete outlier. Anybody guess which choice the ridiculous choice was? I'm going to claim that one of those 5 choices was just completely, actually 2 of them were ridiculous. So yes, 0 is one that's never going to happen because your equivalence, your cardinality of your quotient set is being built from your building set. The only time that you could ever get a cardinality of 0, in other words, the number of equivalence classes is 0, is if you start off with your building set as the empty set. So it technically could happen, but one time among infinitely many possibilities. So the 0 there is technically could be the right answer, but not even close with this example because your building set had 3 elements in it. Now remember, the quotient set is dealing with your equivalence classes of A, and each of your equivalence classes of A comes from the elements of A, which means the maximum number of your equivalence classes is always going to be the cardinality. Well, that was unfortunate. Just a second. I need to do something here. All right. So I am back on the PowerPoint right now, and I'm going to rewrite down what we had before. There we go. Whoops. Slight technological issue on my end. Not really. More of a forgetting what I actually had in front of me open. All right. So this guy here, bare minimum, you can always write your quotient set where you have the equivalence classes of each element. Notice what this means. This means that if you look at the cardinality of your quotient set, in other words, the number of distinct equivalence classes, maximum it would ever be is the number of elements in A, and the least it would ever be is 0. So the 0, 1, 2, or 3 is just getting you inside of that realm. Now remember also what cardinality is. Cardinality is counting the number of objects in your set. So remembering those pieces of information, plus that new inequality, anybody have a guess which of these 5 answers is an automatic don't pick it answer? Yep, you got it. If you see a fraction, please don't ever pick a fraction for a cardinality. Cardinality is what? It counts how many of something you have. So you're looking at positive integers and maybe 0 if you have the empty set, okay? So in terms of legit choices, 1, 2, and 3 were your sort of sane choices if you didn't know what was going on. And based off of what the work we've done so far, we actually threw down 3 objects up here. So if you didn't think about it at all, something like 3 would be just looking at those 3 objects. Now, here's where you actually have to do a little bit of thought. Okay, so I'm going to stop sharing the second screen. So let us go back to what we were working on here. If you're looking at cardinality, if any of these objects are the same, you don't write it down. So we wrote down what each one of those 3 elements were. Our equivalence class of 1, our equivalence class of 2, our equivalence class of 3. Are any of these equivalence classes equal to each other? They are. In fact, the first 2 are equal to each other. So what we have is, since those 2 guys are equal to each other, notice what happens down here in your quotient set, and this happens almost all the time, okay? You typically have at least 2 of these equivalence classes are equal to each other, often more. And what happens here is you can say, hey, you know what, I don't need to write down both the equivalence class of 2 and the equivalence class of 3, because the equivalence class of 2 and, I lie, don't write down both the equivalence class of 1 and the equivalence class of 2. Here, I crossed off the equivalence class of 2. Why? Because it was exactly the same as the equivalence class of 1, so I wrote our set in the normal way. Remember when we dealt with sets in the past, it was when we wrote down the duplicated objects where we wrote it down sort of like it was a multi-set. That wasn't the way that you would read off cardinality. You'd always have to cross off those duplicated sets first. One of the ways to think about it is, I have forgotten now your guys' majors, but typically we have an extraordinarily high percentage of computer science or computer engineering. This is, the technical term is your quotient set here is a way to partition the set A, okay? So if you partition something, you have some original set and you just break it up. Here, we broke it up into 2 pieces, 1, 2, and 3. It turns out if you actually create your quotient set correctly, your distinct equivalence classes will be using up the entirety of your building set A, and it'll just break it up into a certain number of pieces. This cardinality of your quotient set tells you how many total pieces you broke that original building set into. I had one of my students last semester, he's like, That's like partitioning your hard drive on your computer. And I was like, yep, it's basically the exact same thing, except here, well, we've got a set in front of us and it's a lot simpler. Okay? But that's the idea, is you're just breaking this up into pieces. So here, the number of distinct equivalence classes, the number of different equivalence classes would actually be here at 2, because those two are the same. Now, I actually like seeing it off the picture. Notice you can read this same information off of your picture or your digraph representation. Notice if you look at your digraph representation, if you look at the connected components, that's the technical term, but the pieces that are all linked together, where here we had what? We had one piece, we had two pieces. There are no edges, there are no arrows that join between these two guys, so they're two different pieces. They almost look like two different pictures that were just sort of hanging out next to each other. This also tells you the number of distinct equivalence classes. Each equivalence class would correspond to one of these pieces. Notice the equivalence class of 3 is just 3. The equivalence class of 1 and 2 are 1 and 2. It logs what vertices are in the equivalence classes. Okay. You don't have to do it that way, but just letting you know that that is also a way that you can pull this exact same information. Okay. Questions make sense, kind of feeling okay-ish. I'm just looking for ish at this point in time. All right, so next question, and I'm going to throw this next question to you guys. This question is up and pull everywhere, so I'm going to go ahead and switch over so you can see it here on the shared screen. So suppose you have this second guy, and I'm going to make this one a little bit bigger for you guys and get hopefully the words off of there as well. The words didn't come off very well. All right, so for this next guy, why is it not activated? There we are. Now you can see it. Sorry about that. Or you can access it. You should have been able to see it before. So in terms of this guy right here, our building set for this example is going to be the numbers 1 through 5. Our relation is the ordered pairs 1, 1, 1, 5, 2, 2, 3, 3, 3, 4. The one that you can't quite see here that I can't get rid of those guys very well is 4, 3. Then 4, 4, 5, 1, and 5, 5. And I'm going to go ahead and tell you straight up right here that this guy is an equivalence relation. And what we want to do is we would like to determine, and you can't see this. Let me see if I can make this wider. Not easily. So that is not making that wider for us. All right. So what it wants us to do is it wants you to determine the equivalence class of, I believe that's 3 if I remember correctly. Can't quite see that there. By selecting the elements from A right here to include in that particular equivalence class. Okay. Let's see if this helps. It did not even close. So just a second. All right. I was just trying to get rid of the menu. You can get rid of the menu if it's inside a PowerPoint, but not when you're on the actual website. Okay. But go ahead, make your selections, see what you guys think here. You can select as many of those guys as you want, and notice they correspond, the 1 through 5, exactly to the elements that are coming from A. And remember, every single equivalence class is only some subset of A, so these would be the only elements that you're allowed to use to build that equivalence class. I would definitely recommend when you're doing, well, you can only answer it when you actually get into either the website or the app. You'll be able to see all of the covered up words right there when you do that. All right, I am seeing the number of guesses stabilize. Does anybody else want to take a guess, or has everybody made the guesses that they wanted to? All right, I'm not seeing anybody fuss about not being able to. Oh, there's some more guesses. Looks like there was just a delay on my end. All right, it looks like they've stabilized again. That looks like close to the number of guesses that I would expect to come in from us. So let us see what you guys thought. Ooh, all over the place. So it does look like here that there are some clear winners, and the clear winners that I see here are that you guys think 3 and 4 need to be a part of this equivalence class of, which you can't see in the shared screen, but should be a 3. Okay? So anybody want to take a guess on why you would make those selections? And notice I didn't say those selections were right. I just said, why would you guess those selections? Anybody want to take a guess at that? Yep, that's totally it. So if you're trying to find the equivalence class of 3, it is totally, you look at those ordered pairs that start with a 3. You only have the 2 ordered pairs, 3, 3, and 3, 4 in the actual relation. So you pull off those N2 elements of 3 and 4. That is exactly all you have to worry about doing. Now this question did not ask you how many different equivalence classes are there in this particular relation. I'm going to let you guys figure that out on your own, but I'll tell you that there should be 3 of them. I'd write this down in the corner somewhere, wherever you're writing things down, if you're writing things down, and double check to make sure that you can actually get 3 different equivalence classes in the future. Okay? But that's all I've got in terms of equivalence relations. Next thing we're going to do is we're going to go on and look at functions. But before we do that, are there any questions from you guys before we pivot and start looking at functions, which are specific types of relations? All right, well, I am not seeing any questions come in, so let us look at functions. Now, for functions, I do not have a PowerPoint, which honestly I don't think is that big of a downfall for us. So let us look at this other thing with functions. So first thing with functions is we need to define it, okay? I'm assuming that all of you have worked with functions for at least several years of your life, but we're going to look at a couple of very specific type of functions that we deal with in discrete math, or some, if you will, properties of functions, okay? So the first thing is definition. So if we look at a function symbolically, it's typically written like this. Now this is not the actual rule of the function, so we'll talk about that in a second. But this is some symbols that you don't often see until you get up into a college level math. So let me explain these symbols. Before the colon right here, the f, that's the name of your function. So you know how with functions you often have something like f of x equals x squared plus 2 or something like that. This f is the name of the function, just like the f of x back from an algebra or a calculus class would have said f is the name of your function. Okay. The a here tells you what you plug into your function. So a is your domain, or at least the set that the domain of your function is coming from. And the letter over here after the arrow, this is where your function values get mapped to. So this is technically called the codomain. It is the set where the range is a subset of. Okay. Now, you don't need to know all of that terminology right now, although we'll write it out here in just a second. This is the definition of a function. A function is a relation. So, is a relation. such that if you pick any element inside the domain of your function, technically speaking, when you talk about domain, the symbol for domain is typically the abbreviated DOM. Okay. I am assuming that we're all comfortable with what the domain of a function is. It's the things you're allowed to plug into the function. In this connotation, we'll go with A. So in our case, A. Okay. So if you pick anybody from your building set A, anybody from your domain, then the following happens. If you look at f of A, this is exactly one element. And specifically, it is one element from that set B. Okay. So we talked about range a second ago. I'm assuming again that you guys are comfortable with what range is. The range of your function f is always some subset of B, and B here is technically called the codomain. It's called the codomain, co meaning like beside the domain. It's called the codomain because you typically, when you write these guys out, you don't always very, very carefully write out only the elements that are in your range. So your range can be a proper subset of this codomain, is what happens. Okay. Now, notice the key thing here. The very, very key thing here is the exactly one element. Now, we've been dealing with ordered pairs a lot, and we're going to continue on to deal with ordered pairs even when we're dealing with functions, which back in like an algebra-based class is not something they typically do. They normally deal with functions and they say, hey, this is some rule. And that's because they deal with functions that have an infinite domain. Like you could plug in any integer, you could plug in any real number, or you could only plug in positive real numbers. And in that case, it's easier to write your function as a formula. Now, what happens if you have a relation, and this relation is written out as ordered pairs, but you still need to check to see if that relation is actually a function? Well, it turns out you can totally do that as well. Okay, so if we look at this given relation and it has the ordered pairs of 1, 1, 1, 3, 2, 3, and 3, 1, and let me go ahead and insert our building set A. Okay, so and we're going to go ahead and assume our building set A here is the numbers 1 through 3. What do you guys think? Does this look like it could be a function? It's definitely a relation, and functions are relations. So the question we have here is this guy a function? That example right there in red. What do you guys think? Don't overthink it too much. There's only two possible answers. Yes, it's a function, or no, it's not a function. Well, good news is I have guesses coming in. Bad news is they're not the right answer. So let's go back to the definition of a function and see what this actually means. Okay? So it says take anybody in your domain. So your domain is, in terms of your ordered pairs, the first element. So for this relation, the domain, and let's make sure I'm drawing here, our domain of R here is going to be all the first positions. So it's actually going to be the full set A. So it would be 1, it would be 2, it would be 3. Now, the range of R is going to be all of the elements we actually get to. So this one here, we get to 1, we get to 3 in our second position, but we don't actually get to, well, all 3 elements that are in set A. Okay? So if we wanted to write this thing out, we could actually write it out as relation R is going from A to A, but our range is really smaller than A. Now, in terms of figuring out if you have a function, this symbol is different than in terms of the ordered pair. So here's what this symbol means. Each of your ordered pairs, so actually let me put it up here. So ordered pairs have the format of A comma f of A. Huh? Now, if I give you that new piece of information, what do you guys think? In this example right here, are we a function? The key thing is what to look for. All right, so we've got a couple of new guesses coming in. So the answer here is no, it's not a function, and it's because of these two guys. Okay, so what this says is, another way to interpret this definition of a function with respect to ordered pairs is, if you have ordered pairs, if the first position of the ordered pair is the same, the last position of the ordered pair also has to be the same. Notice this here, this f of A, that's talking about your second position of your ordered pair. So the exactly one element tells you that you have at most one ordered pair with the same first position. If we were talking about equivalence classes, which we're not because functions are almost never equivalence relations, but if we were talking about equivalence classes, this would tell you that each equivalence class has exactly one element in it. Okay? In other words here, what are we doing? Because we have these two ordered pairs that both start with 1, this tells us that if you look at f of 1, wow, we didn't name it f, so just a second. Let me do r of 1, so get back up with that. So here, r of 1 would equal either 1 or 3. That's not one element. Therefore, so r is not a function. Now, if we wanted to actually look at an example that was a function, we could do something like this. Maybe we say, hey, maybe we look at relation S. I can still look at the same building set of 1, 2, and 3, but now the key thing to make sure that this guy is a function, let's build ourselves a function. What would be an element that we could put in this second position of 2 right here? And let's assume that our building set is 1, 2, 3. Just to make our lives easier. So what do you guys think? What do you guys want to put in the second position of our second ordered pair, the one that starts with a 2? Sure. If you guys want to go with 4, we can go with 4. I saw we had several options, so I'll pick the one that I didn't think of first off. So we could do this, and maybe you do somebody like that. Turns out if you want to force your relation, your set of ordered pairs to be a function, you can do exactly what we did to start with and just list out a bunch of ordered pairs where all their first elements are different. If all of their first elements are different, it doesn't matter what you throw in for their second elements whatsoever, you're automatically going to be guaranteed to have a function. Now, you may not have a special type of function like you might want, but you're guaranteed to have a function. So this guy here, this would be an example of a function. And that is because all of those first positions are different. And that's it. Okay? That's how to tell functions from ordered pairs. Okay? So let us get into some of the naming conventions that we talk about, or terms that we talk about with respect to functions. We already talked about some of them. Domain in terms of formula. Domain is what you plug into the function when you have some sort of function, formula, rule that you deal with. In terms of the ordered pairs, the domain is the first element. Range is what gets spit out of your function if you have a formula. In terms of ordered pairs, your range is the second element. And then we talked about codomain. Codomain is specifically the set that's on the other end of the arrow if you have this function symbol of f colon a to b. Okay. Now, there are some additional terms that you can have, and the first additional term that you have is something called the image of A, and I've alluded to the image of A, but I don't think I've actually written down what the image of A is. To be really, really lazy, the image of A is simply you plug A into your function, and you get back, well, whatever the function tells you, you get back. So it's like the range, but only when you plug in the value of A. Or if you're looking inside of your ordered pairs, the image of A is going to be that second position. In other words, this image is calculated in a very similar way of if you were calculating those equivalence classes from just a little while ago. The only difference here is, well, you're not assuming that you start from an equivalence relation, we're assuming we start from a function. And while there is some equivalence relations that are also functions, typically there's not an overlap. But that would be the idea of image. It's the stuff you get back once you plug in whatever element you care about. Now, in terms of types of functions, there are, we've got 6 types of functions that we're going to care about, and they're all highly related. So the first one is somebody called an identity function, and depending on the book that you look at, it's got different symbols. So you always have to say the identity function of some set. One way of talking about the identity function is with the symbol 1, and then there's the subscript of whatever set you have. The other really common way of dealing with the identity function is you have a lowercase I, and then the subscript is whatever set you're dealing with. But I believe your book does the lowercase I, but he leaves off the dot, which is also something you see. I'm not sure why they decided to leave off the dot, but it is something you see. Okay, so here's the actual definition or how to define it. I'll go ahead and do I for identity right here in the middle. So you've got your identity function, and it actually goes from building set A to building set A, and it is defined in the following way. If you plug in some little baby element from building set A, and notice here, unlike with other places where we would have, or previously where we would have to say that this little building set A is coming from, this little element A is coming from building set A, because we've already established that our function is going from A to A, this tells you that that symbol has to come from our domain right here. But the formula to get an identity function just says, hey, whatever you plug in, you get it out. Okay? This guy here, in terms of a formula, you've totally seen him before. Y equals X. That's your identity function. Or in terms of ordered pairs, this guy is exactly the same thing as just having all of your doubled up ordered pairs. Maybe it goes out to 5. This is your function that is also an equivalence relation because it's reflexive, and by only having your ordered pairs that are exactly the same, like 1, 1, 2, 2, etc., you're automatically symmetric and transitive by default, okay? Not because you actually had anything you really had to check, okay? But that would be your identity function. It essentially, when you're doing arithmetic, like adding and subtracting, multiplying and dividing with real numbers or with integers, you know you have your number 1 and it's helpful. Well, it turns out the identity function with respect to functions acts like the number 1 would with integers and arithmetic, which is why some people actually call it 1 and then the subscript A. So that's the identity function. Now, we're going to care about some other types of functions as well, and the next 2 types of functions are functions called one-to-one and onto. You often do typically read them out one-to-one and onto in that order, although when I prepped these notes out earlier, I wrote onto first. It's 2 different properties, and these are the 2 main properties that we're going to care about with respect to functions. So a function is onto. So here's our definition of onto, or an onto function. So f is an onto function. We're not checking to see if it's a function. We're assuming that it already is a function, and then we're checking to see if it is onto. So the property of being onto goes as follows. If the range of your function is exactly equal to your codomain. Okay? So let me go ahead and write down. So here's our function. It's going from A to B. Okay? So if the range of the function actually equals this complete set B, so in terms of what you would actually check to see if a function is onto, goes as follows. You look at every single element in B, the set that's after the arrow, and that would have to be given to you. Then you look to see if you can find a corresponding element from your building set A, where, because I don't think I gave you the logical symbols for this, where B equals f of A. And we'll see how to actually use that in practice. Notice, though, in terms of the ordered pairs, this is relatively straightforward to check. If you actually have all your ordered pairs listed out, all you look is in your building set here that's after the arrow. In terms of a relation where you have your relation is from A to B, it's the same idea here with the function. You look at all of the second positions, and if in all of your second positions of your ordered pair, you've used up everybody in this particular second building set, then you would be onto. Okay? Typically, when you have to do a little bit more work to check for onto, this is when you would be given the formula version of your function. So for example, actually let's do the examples after, we'll go ahead and do an example right now. So for example, if we look at some relation and we have something like 1, 2, 2, 4, 3, 1, 4, 3, maybe 5, 2. And let's do a second one of these as well. And I have to give you the building sets, otherwise this doesn't make sense. So just a second, let's do the building sets. It looks here like our domain in both cases is going to turn out to be 5, and then we'll deal with what our building set is. So for this one, let's look at 3, let's look at 2, let's look at 5, 1, and 4. And I need a little bit more space. So here, consider the function, and we have 2 versions of them. F, and it's going to be going from building sets A to A, where A equals 1 through 5. Whoops. That was supposed to be 1 through 5. So here is the big question. What do you guys think? Of these 2 examples right here, is either of those 2 examples onto? What do you think? Is this first one onto? Is the second one onto? Let me actually go ahead and label them. So F and G. So both of these guys are given in terms of the ordered pairs, which is, you got to think about it for a second. So onto is all about your range. It's all about, in terms of the ordered pairs, your second positions. Okay. So here, for the first one, our second positions are these numbers right here, the 2, the 4, the 1, the 3, the 2. We already have a function, so we're good to look at those second positions. Now, if we look at those second positions, our range right here of this function is just pulling those numbers. So notice what numbers there are. We've got 1, we've got 2, we've got 3, we've got 4. Do we have another element? We sure do, but it's 2, and we already wrote down a 2, so we can close this guy off. Now, we just found that our range was the integers 1 through 4. So what do you guys think? Is this function f onto? The only answers are yes or no. Yes, it's onto, or no, it's not onto. What do you guys think? Correct. So this one is not onto, and it's not onto because we are missing what? We're missing that number 5. So that number 5 is not in our range, which means our range is not exactly the same as our building set, our codomain, right there after the arrow, okay? So if you've got somebody you haven't used in that second position, that's totally okay, but the function isn't considered an onto function. Now, using that same analysis, we're going to look at our second function. We'll look at all of our second positions. We'll calculate this range. So the range of function g looks like it's 1, 2, 3, 4, 5. It looks like we've got all the numbers 1, 2, 3, 4, and 5. What do you think? Is this second guy onto? Is function g onto? Only got 2 possibilities of an answer, yes or no. So what do you think? Is that second example, that g function? Yes, it is. You guys totally nailed it. So this guy does equal that same codomain set right here, which means, yes, this guy is an onto function. So those are the 2 examples of what you would see if you're dealing with ordered pairs. I've got another example prepped up already to see how you would tell if you're given the formula if somebody is onto or not. If you are given ordered pairs, the best way to tell onto is looking at the range or your set of all of your second positions in your ordered pairs and seeing if it matches to the set that's after the arrow. Okay. In terms of if you have a formula or some sort of equation, equation is the wrong word, expression, rule, this is the stuff inside parentheses. You have to use it that way. All right, so that deals with onto. The next one that we have is somebody called one-to-one, and let's look and see the definition of one-to-one. Okay, so one-to-one goes as follows, and it says, hey, you start off with some function. So f is a one-to-one, and people often abbreviate one-to-one, 1-1. I know that looks like kind of an H if you're writing quickly, but it actually is supposed to be a 1, a dash, and then a 1. Okay? So that's the shorthand of how people write one-to-one. So f is a one-to-one function. The assumption is you started off with a function, and then the only thing we're checking is the one-to-one part. Okay? if the following happens. If, whenever, all right. If whenever f of A equals f of B, we can track it back and find that really A equaled B. Okay. Now, what would this mean in terms of the ordered pairs? In terms of the ordered pairs, remember the f of A and the f of B is the last part or the second position of your ordered pair. The A and the B part is the first position of your ordered pair. So in terms of ordered pairs, note this means don't use some element of your building set B more than once in the second position of your ordered pairs. Okay. So in terms of your ordered pairs, to be a function, your first position has to be used exactly once. To be one-to-one, your second position has to also be used no more than once. Okay. So if we looked back at our same two examples that we had before, notice we can also check if these guys are one-to-one or on the same functions. So for example, for this one here, what happens? If you've got matching things, notice here we've got 1, 2, and 5, 2. The second positions match. That would tell you that f of 1 equals f of 5. Okay? But do their first positions match? And the answer here is no, their first positions don't match. So this guy turns out to be not one-to-one. Okay? Now, in this second example, notice all of our second positions are different. So you never get into this situation where you've got two guys that are same where the first positions are different. So you're good to go. This guy is both one-to-one and on-to. So that was attempting to be my symbol for and. Okay. In the case where you have a finite number of ordered pairs, it turns out if you're one-to-one, you're automatically onto and vice versa. In other words, both of them work or both of them fail. The situation where you can get one and not the other one is where you actually have two different building sets. So two different building sets, or where you have sets that are infinite. But if you're coming from like what we did here, where you're coming from the exact same building set, and it's a finite building set, you're either going to have both of them or none of them is what has a tendency to happen. Okay. All right, so that would be one-to-one. And we should end with one more example of one-to-one and onto. But before we get into that next example, let me go ahead and give you the next definitions of functions that we're going to care about. That way you have all of them together. Okay. So we also have what's known as an invertible function. So this one here is f is invertible. The assumption is you start off with a function. If the relation f inverse is also a function. Now remember the symbol of f inverse. What did it mean? It just means that if you have the ordered pair A, comma, B, and F, you flip-flop the order of your ordered pairs to get your inverse relation. Okay? So building your inverse function is almost identical to building your inverse relation. The only thing that's different is after you flip all your ordered pairs, you then go back and check to see if you still have a function. It turns out the only way that you're actually going to still get a function is if you started with a one-to-one function. It's the only way the inverse will actually stay a function. So a criteria to be an invertible function is you have to be one-to-one. And if you ever recall finding invertible or finding the inverse of a function back in like an algebra class, sometimes I do it in a calculus class as well, because you're looking at derivatives of invertible functions in those formulas. One of the things that they'll say is the underlying criteria is you have to be a one-to-one function, and if not, you restrict the domain to make it a one-to-one function. So in terms of what we need, you reverse the ordered pairs. Now, here's the first fancy word that we have. So a function is called a bijection, bi here meaning two. The jection part here is referring to a function if it is both one-to-one and onto. So F is a bijection, or called a bijection, or is bijective if it is both one-to-one and onto. One-to-one and onto also have their own fancy words. One-to-one is called injective. Onto is also called surjective. So these guys actually have three names that all sound very similar. The prefixes here totally came from French. But the sort of standard is to go ahead and talk about the just one-to-one and onto. Okay. So that would be bijective. The other thing that we want to go ahead and do, and let me go ahead and put it in here now, is a specific type of bijection. So let me include this. If you note, a bijection, so it's both one-to-one and onto, from set A to set A. And this type of bijection is typically denoted with a P. So in terms of symbols, it would look like this. So very, very similar to the examples that we just had. Okay? And this guy is called, so if the two building sets are exactly the same set, and it's a bijection, that function is called a permutation function. Or just a permutation of set A. The definition here is permutation. So one of the big things that we're going to be looking at in this Chapter 5 section, which is where we're currently living with functions in your textbook, is we're going to be looking at these permutation functions. Permutation functions have to be both one-to-one and onto, and your two building sets are A. Please notice if you go back to the examples that we had before, our example here at G was on the same building set A. That was the integers 1 through 5. It turned out to be both one-to-one and onto. This guy right here is an example of a permutation function, a finite permutation function, because we're on a finite number of elements. Okay. So let us now look at an example of somebody who might be a permutation function, but get to looking at the function notation and what you do with functions when you're in the infinite case. And based on time, this is probably going to be close to our last example for today. Okay. So let me leave the definition up here. So actually, let me just copy down. So permutation function, this one here, we need to be both one-to-one and onto, and then I'll hide that part up top. All right. So we've got this function. We're going to call this function f because we're lazy and we typically call functions f. It's going to go from the set of integers to the set of integers. So this means the domain of the function is z, or integers, and the codomain is also z. I don't know if the actual range is z, but the range is some subset of all integers. Okay. This function is given by the formula f of a, and I pulled a here to indicate that we're pulling strictly from the set of integers. It is often standard to use x, like in other courses that you guys would have had, but often when you first get into this sort of area of math, if you see an x, internally your head is thinking any real number works, and that's not. Right now we're only allowed for a's here to be plugged in to be integers. Okay. The formula for our function is 3a minus 5. We're not asked to verify that this is a function. We're just told it is a function. Please note, if you have a formula, and your formula isn't some weird piecewise function doing craziness, you're pretty much guaranteed that it's going to meet the criteria of being a function. Okay? Now what we want to determine is we want to determine if this function is a permutation function or a permutation of z. And the thing that we would need to do is we'd need to check to see if this function is one-to-one or onto. I personally find it easiest to check one-to-one first, just because I think one-to-one is easier to check. And also, if it fails to be one-to-one, you don't have to move on to checking to see if your function was onto, because it's definitely not a permutation function because it was not both one-to-one and onto. Okay. So if we want to check one-to-one, I'm just going to go ahead and box it just to sort of give ourselves an idea of what we're doing here. Here's what we need. If f of a equals f of b, we have to have that a and b are equal to each other. Okay? So first thing you do is you just say, hey, let's go ahead and assume we actually have the if part of this statement. So we'll assume, and this is what you do anytime that you check if a function is one-to-one, if you have a formula for the function. Okay? Now, once you've assumed that f of a equals f of b, you plug in your formula. Your formula says f of a is 3a minus 5. Your formula for f of b says 3b minus 5 is f of b. And now we're going to solve for either a or b. It doesn't matter what you focus on. I'll solve on a just because it's on the left side, and that's normally the side that we solve for. Okay? So we'll add 5 to both sides. So we get 3a equals 3b. We divide 3 on both sides, so standard algebra here. And if you divide 3 on both sides, you'll get that a equals b. And notice, what does that tell you? That tells you that the function is one-to-one. So that was what we wanted to get. Now notice here, we want this thing to be a permutation function. So we have to check not just one-to-one, we also have to check if the function is onto. Now with onto, we don't have ordered pairs anymore, or if we did, we have infinitely many ordered pairs. So here what we do is we say, hey, all right, well, I've got to deal with this formula, so this is where I deal with that other string of the other way of talking about the definition of onto that we haven't dealt with yet, or we haven't played around with yet. So this is what we need. We need that for every b in our codomain. So everybody after the arrow, in our case, this is an integer. So for every integer, there exists some other integer a, so somebody from the domain, where, or such that b equals f of a. Now, we have a formula for f of a, so I can actually cross off f of a and actually put the formula. The formula here is 3a minus 5. Okay, so that's what we need. Now, here's what you do. With onto, you typically have scratch work. Okay, it's something that you would put to the side that it's not actually part of the logical flow, but you got to do it a little bit of scratch work so you can get to writing this up. Okay, so scratch work. So we need results. Okay, so we start off with b equals 3a. This is supposed to work for any b. We'll be able to find some a that makes this work. So what we're going to do is we're going to solve for a. So if we solve for a, what happens? You add 5 to both sides. You divide by 3 on both sides. And now you've got a sort of template for what you want to do with a. So what do you guys think? Did we actually get to an onto function here before I write up the answer? What do you guys think? Is our function, that's the 3a minus 5, is that guy going to be onto? Did we meet the criteria needed right here? The answer is either yes or no. I did activate it and poll everywhere, so you don't have to answer via chat. You can totally answer. Oh, no, it's slightly different. I didn't put this one up. I put the adjusted form up. So I'll leave you guys to answer the adjusted form after class, or at least something to think about after class. The difference on the one up on poll everywhere is it's got R instead of Z, so real numbers instead of integers. But definitely something to think about. So here's the issue. This is not onto, okay? So this one isn't. So I'll let you guys look at the one that's got real numbers and see if there's a change. But notice what happens. This thing that we got for A, we're supposed to have that A as an integer. We're supposed to find some integer that you can plug into our function to get back B always being an integer. Well, if B is always an integer, we've got some formula where we could find A. That's no problem. But are we guaranteed that that fraction is always an integer? The answer is no. So not always a fraction, not a fraction, not always an integer. Sometimes it's a fraction. So this is where you can actually throw out a counterexample. So pick B to equal, I don't even know, how about 0? That'll give us a nice fraction for A. So pick B equals 0. Then A would have to be 5/3 in order for 0 to equal what? To equal F of 5/3. Okay? But since A is not an integer, this means that our original function F is not onto. Now, you guys have already been looking at this exact same question, but where the only difference is we're no longer dealing simply with integers. That new adjusted function where you're dealing with real numbers, it would still be it would still be 1-to-1 because all of this same work would be exactly the same. But the question is, would it now be onto? And the answer is the scratch work would be exactly the same. You'd still be able to solve for A. You get this expression. But is there any issue now if you change out the integer sets over to real numbers? Is there any issue with this guy, this expression for A not always being an integer? Huh? So let's see. What did you guys think? It was kind of split, but the vast majority of you said no, it's not a permutation function, and that would be the correct answer for the one with integers. Now, if you go back and redo the problem with real numbers, so conclusion here, let's go ahead and wrap up the conclusion, then F is not a permutation function, but if you switched out F for real numbers, that's not a real number. If you switched out to real numbers, same expression, so this is F of 3r minus 5. This guy is, so it is a permutation function of real numbers, and that is because this part right here, well, if you start with a real number, add 5 and divide by 3, you still have a real number. So one of the things that happens with these permutation functions is it totally depends on what your building sets are, whether you actually turn into being a permutation function or not. So you're always watching out for, do I have the right format of my numbers? 1-to-1 has a tendency not to change too terribly much with your building sets, although that's a little bit of a lie. Depending how it changes, the 1-to-1 can also change. But onto is the one that you have a tendency to see fluctuating a lot more quickly if you change your building sets. Okay, so that's a crash course in terms of functions. Sorry we went over time just a little bit. So next time in terms of what we'll do, we're going to focus in on finite permutation functions, and the whole time, next time we'll talk about finite permutation functions. So that is it for today.